So, my calculation is done now. Okay, let us first open the output file with ChemCraft. So, here you can see one imaginary frequency, it comes with negative, we should not, we have discussed before, we should not call it a negative frequency, it is an imaginary frequency. And now if we view the frequency, you can see this corresponds to actually the reactant coordinate. So, this is fluorine, this is chlorine, this is how the reaction is supposed to happen. Do not get fooled by this bond, this is just representation. So, one important thing to notice is that getting one negative frequency is not good enough. The frequency should be a high enough value. If a negative frequency is below 200, 300 maybe, mostly it is a rotation or torsion of a bond that generally does not correspond to any chemical reaction or the internal coordinate corresponding to the reaction. But this actually at 500 and this looks like a proper if you visual. So, always a good idea to visualize the frequency and see that is it connecting the reactant and the product or not. There is a more better way of seeing that this is a real good transition state or not. Remember, getting a transition state is not good enough, it has to connect your reactant and your product. Maybe a good idea to look at the output file what this second step done. So, we have done a two-stage process. First step we have done a scan, and once we confirm that we are close to the transition state of the saddle point, we now ran a transition state search job. So, this was my input file. So, once we have run the calculation, so in the first geometry optimization cycle, what it will do is that it will calculate a numerical frequency by calculating the gradient, and from this frequency you can see that this only one imaginary mode, and generally it follows the first imaginary mode. If after the output, if you get that the imaginary mode is somewhere below, so there is a keyword which can where you can specify to follow not the first imaginary mode, but the second or the third imaginary mode. You should see the outcome manual for more details. So, once your calculation is done, then it will start doing the geometry optimization step. So, by second cycle that is almost converged, and after the third cycle it is completely converged. So, now it will do a frequency calculation again. And now it will do the final imaginary mode what we have seen, and of course, it will do the thermochemistry analysis. Now, so this is a case where we were sure that we already know the internal coordinate which is correspond to the reactant coordinate, but that will not be always the case. For polyatomic molecule, it will not be often be easy enough to find out the internal coordinate which actually correspond to the reaction coordinate. So, for that you need to use a modern technique which is called the nudge elastic band. What you do in the nudge elastic band is that you find out a minimum energy pathway connecting the given reactant and product state minimum on the potential energy surface, and thereby estimate an activation energy of the transition state. The path can have one or more maxima, each one corresponding to a first order saddle point, and the NEB method offers an advantage over eigenvector following method which we are doing before, that it is guaranteed to find a saddle point that connects the given reactant or product state, but sometime what happens is that it will not converge to the proper transition state. So, you have to see that it has converged to a proper transition state or not. That is the, so it may be a saddle point, but may not be the saddle point connecting the reactant. The minimum energy path is often used to represent the reaction coordinate of the transition between the two states, and what is done in this process, an initial path is generated and represented by a discrete set of configuration of atoms referred as the images of the system. If you want to see the images, what you want to suppose this is my initial system and this is my final system, this is a Diels-Alder reaction. Maybe we will try to study it at one point of time. What will happen in this case is that, so this will actually generate the variety of images connecting the reactant and product, and each of these intermediate images is connected by a spring kind of an approximation with the previous step, and whatever is the maximum in this among these images generally correspond to the transition state. So, to find out this one, we will use this input file. So, it is PM3 NEB-TS frequency, you have to give the reactant file and as well as the product file. So, we already have certain files from before. Now, we will just make a good use of them to generate the reactant and the product. So, I believe we have done the. So, this we will find out the optimized transition state for the same chemical problem, but now with the nudge elastic band. And so, here first I have to generate the reactant and the product. We have, this was my initial structure for the reactant. Good idea will be to open it with Chemcraft, because Chemcraft is generally good for doing this kind of manipulation. So, this is my reactant minus the chlorine atom. Now, I have to add the chlorine atom. So, add atom, this is my chlorine, I put it here. Two things I have to make sure. Because at the reactant what should happen is that first of all it has to be 180 degree or close to 180 degree, will make my transition state finding easier. So, let us first fix the angle. And this is 175, we are almost there. So, let me check the distance now. It is 1.84, maybe it will be a good idea to increase the distance a little bit more. Or we can use this one, we can select this one, we can go to drag atom command and we can drag the atom a little bit more. So, this can give me a good idea of my initial reactant geometry. Of course, I have to optimize it. So, I save structure as my XYZ. So, now I will directly write it as reactant. Dot XYZ. So, once I get my reactant dot XYZ, I can make an input file which can be very similar to this one. Only thing I have to remember that now I will optimize it to the reactant. I do not need the numfreq because most probably it will go to an this one. It is a good idea to give an initial Hessian, but recalculating Hessian at each 5 step may not be necessary. And of course, now I have to write the thing as reactant dot XYZ. So, this one I will save the name same as reactant. So, that I do not really need to change anything. Says wrong number of argument. Let us see where is the wrong number of argument. Maybe here. Okay, I know the problem. What has happened is because I have generated the initial XYZ file, the reactant.xyz file using Chemcraft. I believe I have discussed this before. Oh, I don't want it to open with Chemcraft. What I want to open it with is Notepad. Now you see the main problem. So an XYZ file format by definition should contain the number of atoms at the first line, and the number of atoms here is 6. So, and it has to have a space line or a comment line afterwards. So now I have saved it with the proper format, and that's why it was initially giving me the trouble. I hope now this will run properly. So it has started calculating the numerical frequencies. Okay, few things to tell here is that the order of atoms in reactant and product must be same. So you have to make sure while you are preparing it that your order of atoms has to be identical irrespective of how you are preparing it. So that means it's a good idea to start either with the reactant or the product, first optimize that structure and then modify, let's say start with the product, and or here what the way we are doing is that we are starting with the reactant, we are optimizing the structure. So I have a good reactant structure, and for the product what I will do is that I will change the reactant structure to look it like a product structure. So that my atoms order in reactant and product will be same. So if the atom orders are not same, if the Cl goes let's say in the first position instead of the sixth position, then the NEB algorithm will not be able to find out the transition state. So one has to be very careful about it. So this is my input file. Of course, you can give here, we are not going to give it, but in some cases if you know how the TS looks like, you can give a guess of the TS structure by using this command, the NEB-TS XYZ file as the name of the guess structure. Also the reactant and product will not be optimized during the default run, but you can make sure that you are using the same method you are choosing for previous optimization. So the method you are using to run the NEB-TS algorithm, you should optimize your reactant or product in the same level as this one. Otherwise what you can do, you can use the pre-opt end is equal to true in the percentage NEB block. We have discussed that the order of the atoms in reactant and product must be same. In some of the cases the named job may not converge to the given number of iteration. So in that case you should take the highest energy image in the path, it will be very close to the actual reactant. Don't go by this number, but this may be for this particular case, but generally this highest point, the highest energy image is very close to the transition state structure. So if you are, even if you have not converged it, you can take the highest energy image and then you can actually run a separate opt-TS job to find out the saddle point. So my frequency calculation is done. I believe it's now optimizing. I believe it's going towards convergence now. No, it's flip-flopping between two structures. Maybe I would have recalculated the Hessian after maybe 10 or 15 step. Or maybe I could have optimized it using XTB before, because generally it's faster. So it says that it has reached the maximum number of optimization cycle but not converged yet. So what I will do here is that means my initial structure is not good. So if my initial structure is not good, then I will first use an XTB to opt. And I will use the recalculate Hessian keyword also, because to calculate an XTB Hessian is super fast. So I think my initial structure is bad. Let us open the initial structure once more. Sometimes this kind of problems can happen. The bond length is not the problem. The angle is also not a very problematic thing. Maybe I can increase the distance a little bit more to make it a 4 angstrom. And this may give me a better starting structure. I keep the name as reactant. I should not forget to open in Notepad and make the number of atom to be 6. So this kind of technique sometimes you need to do. So now I have saved it, and I hope that this will do the calculation a little faster. Oh, it was almost there. So that was the problem. My initial geometry, this one was more closer than it should. The chlorine atom was more closer than it should, and that was maybe the source of the problem. So now it says that the convergence has happened. So what I will do here is that I will start with now the reactant structure. So my reactant is optimized, so I will go to the reactant.xyz file. I will open with ChemCraft. So this is my reactant. So now I will use this one to make the product, because as we have discussed that the reactant and product should have the similar atom number. So now I will add between this one, and I will make the distance was like 1.7. 5 was 1.7 something was there for the product. So this is what I set, and I would increase this distance maybe at 4. Up top, this one has 4, this is fine. I have to increase the distance between these two because it has reduced. So it's 1.7. So this can be my product. So now I write as save as product also. Remember again, I have to now give it the maybe I have not saved it in a proper place. Why it has not went into this? You have to be very careful where you are saving. No, so maybe this time I have saved. Again, it will have the same problem, so I have to open it with Notepad and give the number of atoms. So now just think, my reactant was optimized at XTB level because I wanted a good guess. My product is not at all optimized. So now when I want to make the NEB input file, maybe this is not very clearly visible. Once I copy paste it, maybe it will look slightly better thing to understand. So you see that lines. So first line is PM3, the method. The keyword for the NEB is NEB-TS, and we need to calculate the frequency at the end to make sure that I have opted into correct one. So the percentage NEB block, it gives the end NEB end XYZ file, which will be my product.xyz. I have saved my product structure as product.xyz, and my starting structure is reaction.xyz, that I have also saved. So the only problem is that none of them is optimized at the PM3 level. So what I should do, we should give this keyword PM3 optend is equal to true. So first it will do an optimization and then it will start the NEB calculation. So let me make the name of the input file as neb.inp. And I am good to go. Okay, it says some non-ASCII character from your input file. Maybe because I have done this copy pasting here. There is some non-ASCII character. Now save it. I hope this time this problem will be not there. There may be something more. I don't see any of it, although. So this is called a VI editor. I am just making sure that there is no non-ASCII character. Both of them look fine. Oh, so see the atom order here in the reactant and the product, they are same. Carbon, hydrogen, two hydrogen fluorine, another hydrogen chlorine. I believe now the things are fine. So still showing the problem. Let us see the neb.output file. Maybe it will tell me where the non-ASCII characters are there. Line 4 on product.xyz. 3, 4. At least I don't see any problem. Maybe I will save it again. Save as. Okay, I replace it. I go to the product.xyz file. I open it with Notepad. This should solve the problem.